Hello, I will demonstrate ParkOptimizer. Let's just start it up. And I have made a demo project. So here we have ParkOptimizer, and the workflow will be from loading data from WinSim, and then gradually work our way from general to energy map, impose constraints, make a layout optimization, and then assess the optimal project size. So let's select a WinSim project. I have made one demo, and here, let's see, it's Avia demo. I select the WinSim file, the project file, and then it will find also all the other terrain file and the associated files. So I will also specify data. I would like to look at the 80 meters height, the wind speeds there, and also plus minus 30 meters. I will be analyzing 12 sector. We can analyze more sectors, but not for optimization at the moment. So for optimization, we restrict it to 12 sectors, but for other analysis, we can also use more sectors as well. Okay, so let's import planning area. You can also draw a planning area or open some text file with polygons, just coordinates. Once we've done that, we also must make sure that we have the correct UTM zone, which is corresponding to the VRG file that we will later load in, and also the map of the area of interest. Let's look at set the directory where we will store the results. We can define that. And now we can import the VRG file. Now we want to establish an energy map for our optimization and analysis. So the energy map can be found under layout, LTC, layouts in the WinSim project folders. So I import the VRG file, take some time to read. Then you can choose to perform density correction of the VRG file, and depending on whether it's a pitch or stall turbine, then it's also possible to perform icing correction if you have enough data for that. So let's import the turbine. I will select the Siemens turbine. It's a PWS file, so that should be familiar for WinSim users. And now we can calculate the energy map. What you should also observe is that we have narrowed the analysis to only to consider the planning area. So now the results has been processed, and we also store the energy map as a CSV file in the results folder. So we can look at the energy map as a colored map. It's possible to change color maps to, let's say, to hot. We can also change the scale. Like this. And let's move on to constraints. Now, constraints can be environmental constraints. We can add shapes or draw areas that are excluded. But the core of ParkOptimizer is that we can generate IC exclusion areas based on the IC standard. So the IC constraints are flow inclination, shear, turbulence intensity, and extreme wind, and of course a couple more. But we have focused on these, and terrain inclination is not really a constraint by IC, but it's still is practical. Okay, so I have been setting the constraints here. I choose class A turbines for turbulence intensity, and so I have defined the constraints, the limitations. Now I can map out areas like flow inclination and terrain inclination combined, and we can extract areas where the flow inclination and terrain inclination constraints are violated. So these are the gray areas. So this is the difference with ParkOptimizer compared to other tools, is that instead of checking the constraints after you have placed the turbine, after you have a layout, then for larger projects it's better actually to map out all the unsuitable area you can map out from the beginning on, and then you can focus on where you should put the turbines. So we flip this around. We map out unsuitable areas for site suitability. Then we can continue working on the layouts within the suitable areas, like the white spots here. Another example, shear. We can also add that. And that's why the software needs to read 3 different heights. So here we can see the shear. Turbulence is another feature. So all these can be combined. For the turbulence, we need to import climatology data, and we import TWS files for this purpose. We can set a set of parameters here for turbulence calculation. If we focus on only the wind speed being 15 meters per second, let's do that. And we can also define, when we calculate the characteristics turbulence intensity, whether we want to set the complexity index to 1. That means that the standard deviation part of the turbulence is actually increased by 15%, because there are more 3-dimensional variations in complex terrain that is not accounted for in the, otherwise in the standard. So let's calculate the turbulence, and we get a turbulence map here. We can also calculate turbulence without mass measurements. That means we are using the kinetic turbulent energy from WindSim directly. So we can actually also calculate turbulence from WindSim. What we do here is to combine the turbulence map from WindSim with the turbulence data from the mast. So we do this in the same way as, let's say, we calibrate the wind map with data, turbulence with the wind speed data. And we have different methods for this. There is a couple of methods to choose between. Extreme speed is quite time consuming, so I will skip that, and only the ones with strong computers would have patience to actually map out extreme wind maps. Okay, so these maps can be saved and opened to a file, a CSV file. We can also import shapes. Let's just include some constraints here. Now we could import a shape, which would be constraint. We can do some drawing also. So I will draw this constraint here, saying that maybe here there will be a power line. So we will restrict this area, and let's call this power line. So now you can see that this area is also gray, in addition to the other constraints. Now that we're happy with our constraints, then we can move on to layouts. So now we have the white areas remaining that we can place turbines on. So we have two options here, Basic Optimizer and the Wind Farm Designs Optimizer. Now this one has been undergoing a lot of changes and work, and this one is actually an API service. It's actually done outside it's a web service. So let's use the Basic Optimizer, and we can choose a number of turbines. I will just use a few turbines now. We can choose elliptic distance constraint, and I have made for this turbine 5 by 3 rotor diameters, and the orientation is 300 degrees for this. Here is a possibility to use effective turbulence, but this is a heuristic optimization. So if you have many turbines with lots of turbines, this will probably not end up with a solution if you have a squeezed layout. I can include weight loss and weight loss iterations. Let's just have 2 iterations. We select rotor diameter, and this one should probably be a little bit less because we are dealing with complex terrain than the standard parameter. Now I can start optimizer. So okay, let's put 4 turbines and start optimizer. Okay, so now we have completed the optimization, and the results are stored in wake effect adjusted under the opt-out folder. So here we can see there has been an optimization with only 1 turbine, 2 turbines is layout 2, 3 turbines is layout 3, and 4 turbines is layout 4. So as you can see, the turbines, they actually change position. They don't have to be in principle. Where you put 1 turbine will affect all the other turbines. So this was a short optimization, and now it's writing some summaries. Let's have a look at the results folder. So we have one folder called opt-out, and under there has been a wake optimization. So here is actually, let's see, I think it's finished with the summary log. Here's a summary of the optimization. And this is layout 4. We have as OWS to import to WinZim and as a plain text file. So let's just have a look at how it is. So this is basically just coordinates and the hub height of the turbine. So this can conveniently be used and imported into other tools like WinPro or WinZim or OpenWin. Another feature is the energy curve, which is quite unique. Since we optimize for each size, we get this and a total energy per project size. So this can be useful for determining the optimal size of a project. So let's just go back to the simulation. So the list we see here is corresponding to an energy curve. So let me load a bigger project. I can open a layout from a previous project. So let's see. Okay. I'll just take this with 1,000 turbines. So here I have 10 turbines. Okay, I will import it once more. Open. I can open a layout. Let's see if I can find it again. Yeah, so here I found a layout from a previous optimization, and as you can see, there is a list of actually 15 layouts. Layout with 1 turbine, 2 turbine, 3 turbines, etc. So what we can do then is to go to economic optimization and see how the energy production increases with the project size. Then actually now this is heuristic optimization, so but in theory it would be marginally diminishing. So if we, for instance, have some higher costs than what is actually the price or the revenues from production of the turbines, then it will actually be let's see, we will experience a diminishing curve here, and then it's not optimal to maximize the total size of the project, but you should actually have a smaller size. I will just illustrate with some, let's see, some higher operational costs. And this is specifically valid for complex terrain where you have a lot of variation in the wind field within the site. But in flat terrain, you don't have the same effect. You have more equity, more equal wind all over the site, so you don't have this effect. But here we can see the profitability is let's see, is diminishing. Let's see if I have some higher costs. We can see that even you will lose money if you increase the size of the project. Of course, now this is not profitable at all, but you can imagine that the effect of increasing the weight classes and finding less desirable positions for the turbines, that will actually reduce the profitability of the project when you squeeze in more turbines. So this is useful for assessing the size of the project, and particularly also do a risk assessment, because if you don't really increase your revenues a lot by adding more turbines, you will just basically increase your risk because you pay the same for poor performing turbines at bad spots as you do for better performing turbines, but you don't earn that much more money. So this was a demonstration of ParkOptimizer. Then there's also more to it. We have here some reporting functions. So here we have the whole layout for a project, and you can make IC reports. You can adjust the graph here as you want with colors and ranges of the color scales. But more importantly, you have a reporting function for the IC constraints. So let's just go to the constraints and include extreme wind speed. We just select climatology for that. Now, in this report, let's see. You can get a printout of the IC constraints that is calculated for the specific turbine locations. So when I go save now, it will start writing IC suitability test for each turbine position. So I think I have an example of the similar files, IC reports. Let's see. I will include one result. Let's see. Here's our report. No. So here you can see a small report with um, just 3 turbines. You have the weight loss, you have terrain inclination, flow inclination, shear, ambient turbulence, extreme speed, and effective turbulence that can be calculated.